Rounding off our focus on second order differential equations this month on this channel, let's take a look at proving the situation where you have a second order differential equation with repeated roots and its auxiliary equation and the format of the solution you'll get as a result of that. So ultimately we are just generalizing that result that we have dealt with at least numerically in other videos on this channel before, but just to confirm, if your auxiliary equation has repeated roots, then you know the structure of the solution will be this: y equals ax plus b lots of e to the power of that repeated root from the auxiliary equation, lots of x. But before we continue on any further, I must give you the usual warning, which is, yes, as usual, you're not meant to know this proof for the further maths A-level exam. We're just doing this for fun, for curiosity, all of that. So hopefully you enjoy it too. But what do we need to know in order to be able to do this proof? Well, the same things we needed to know practically as the part 1 video of this content, which was we need to know how to solve a first order differential equation by separation of variables. We also need to be able to solve a first order exact differential equation, and then also we need to have an understanding about how quadratics work to the point where we can rearrange a quadratic that's got repeated roots into the format, as long as it's a quadratic equation mind you, where it's got a coefficient of 1 in front of the squared variable, and therefore if you do that you know that the remaining two coefficients are going to be related to that repeated root in the structure you can see on the screen right now. Okay, that's what you need to know. Let's get on with the proof itself. So let's start by defining some things. We're dealing with a differential equation that looks like this, and then the a, b, and c are real constants. Those are our coefficients to each of those parts in the differential equation, and because we want our differential equation to have repeated roots in its auxiliary quadratic equation, we know therefore b squared minus 4ac must equal 0. Nice. So the first thing we're going to do to make our life a bit easier is we're going to divide both sides of the equation by a, because that will give us that much wanted coefficient of 1 in front of the d squared y over dx squared. Next, just like when we're solving a quadratic, even though this technically isn't a quadratic in this format, we are going to think of two numbers or two things that multiply together to make the coefficient at the end, so two things that multiply together to make c over a, but add together to make b over a. But because it's all algebra, that's a bit weird to do. So I'll just tell you, we're going to split up that b over a as minus b over 2a minus b over 2a. Because of course the minus becomes a plus, and b over 2a plus b over 2a is 2b over 2a, which is b over a. So those middle two terms are still combining to make the correct amount of dy dx that we need. And weirdly, minus b over 2a times by minus b over 2a does equal c over a because of the restrictions we said earlier. We pointed out that b squared minus 4ac was equal to 0, and therefore that means we can do some rearranging to that fact, because we can therefore say that b squared must equal 4ac, and if we divide both sides of that fact by 4a squared, because a has got to be a real constant that's not equal to 0, otherwise it's not a second order differential equation at all, then therefore we have b squared over 4a squared equals c over a. Which is cool because b squared over 4a squared is secretly b over 2a all squared, or minus b over 2a all squared. So therefore, indeed, minus b over 2a is also what you need to multiply by itself to get the c over a on the end here. So we have split it up just like you would split up a quadratic when factorizing it. Cool. That's been really helpful because we can now do a substitution. That means we don't have to deal with these a's, b's, and c's everywhere. We can just say let p equal minus b over 2a, because that means we can now write all those a's, b's, and c's only in terms of p's, using that structure that we have kind of already indicated with that stuff before. So, now that we've done this, we can actually get on with solving the differential equation. We can factorize the third and fourth terms because we notice they both have a factor of minus p. So, factorizing minus p out of both of them, you'll get a dy over dx minus py inside the brackets. But then, the first and the second term can also be rewritten because we realize that secretly, that's just dy over dx minus py differentiated with respect to x. So, we can write this. That's really helpful because it means we can do another substitution. Sorry, a lot of substitutions because this is all very algebraic, so it helps tidy things up as we go. So if we let k equal dy over dx minus py, we can rewrite our differential equation as dk over dx minus pk. This is just a separation of variables differential equation. Worth pointing out once again, the p is a constant, whereas the k is a variable. So therefore, let's rearrange this differential equation. I've done two steps there. I moved the pk over to the other side and then divide both sides by k. Because that means everything's in the right place to now enable me to integrate both sides with respect to x. So if I do that, I'll end up with, on the left-hand side, a ln of k, and the right-hand side, the constant p will integrate to p lots of x, and then because we're integrating, we need an integration constant, so we've got a plus c there. We can then rearrange to make k the subject of the formula by doing e to the power of both sides, but then we don't like the integration constant, the plus c, in that power, so using index laws to split that up, and then rewriting e to the power of c as just a, so that tidies up even more. But we're not done, because although that is what k is equal to, we didn't want what k was equal to, we want what y is equal to. So, realizing we already related k to y using the substitution we defined earlier, we can combine these two things to say we've got this differential equation. dy over dx minus py equals a e to the px. Nice. So, therefore, now we can solve this differential equation. Unfortunately, this isn't separation of variables, it's a first order exact equation, but we still know how to solve them, so it's not too much of a problem. We of course realize that the coefficient of y integrates to get the integrating factor, which is e to the minus px. So that is our integrating factor that we're then going to multiply both sides of the differential equation by, which gets us this. The right-hand side is actually very nice because e to the px times by e to the minus px is just going to be, well, 1. So therefore we're just left with one lot of a on the right-hand side. And that means we can now go ahead and integrate both sides of this differential equation with respect to x. Because the neat trick as part of first order exact differential equations is once you multiply through by that integrating factor, you already know the left-hand side will integrate to y lots of the integrating factor. We also need to integrate the right-hand side, so now let's integrate that a. It's just a constant though, so therefore it's just going to integrate to a lots of x, and then because we've integrated now a second time, we need another integration constant, so let's call that plus b. And guess what? We're practically done. One more step to do, which is to rearrange this to make it y equals by multiplying both sides by e to the power of positive p lots of x, which will mean we end up with ax plus b lots of e to the power of px. And we've done it. There you go. Isn't that neat? I love the way the things cancel out here to make that ax plus b. Really, really cool. So, we're done. And if you thought that proof was pretty neat, then please do like the video, subscribe to my channel and turn notifications on so you can stay up to date with all the proofs and general extension maths videos that I do on this channel. Also check out another video in the Prove It series, there's a link to it on the screen right now. Goodbye!